Today our speaker was Professor Ari Laptev from Sweden.
So the second slide is about the fact that I wanted to say that we have a book which published last year in November, and this is about eigenvalues of and then Lieb-Thirring inequalities. So the thing is that during the last 50 years, the theory of Schrödinger apparatus and respective spectral inequalities, it sort of became a part of analysis because it involved a different part of analysis, and it's really became a very deep theory. And then this is a 500 pages book, which is we tried to collect most of the results, but we couldn't collect everything. Anyway, I wanted to advertise this book and just to mention it. Now, the next slide. So what we have is we shall speak about let me describe what it is about. So we consider Schrödinger apparatus, which is minus delta minus V of x. And then we know that if potential V, electric potential V is equal to 0, then the spectrum of the Schrödinger apparatus is continuous, and it's from 0 to plus infinity. But if we subtract the positive potential, which might be positive, then it generates some negative eigenvalues, which we denote by minus lambda 1, minus lambda 2, and minus lambda n. So what Lieb-Thirring inequalities are about is that they sort of give us energy levels of the sort of quantum mechanical system, and then we take sum of the lambda j to the power gamma. In fact, gamma is equal to 1. It's the most important case because that corresponds to the full energy of the system. When gamma is not equal to 1, it's a little bit more sort of theoretical, but it's because gamma, or even gamma equal to 1, the other sort of situation when gamma is not equal to 1, it helps to find the sort of solution of the problem when gamma is equal to 1. So what Lieb-Thirring inequality is about is that what we want to estimate this is sum of the eigenvalues to the power gamma through negative eigenvalues to the power gamma through the phase volume. And what we have with this phase volume is that we have this constant, and then we have a potential to the power gamma plus d over 2, d is the dimension of the space. Now, these constants are not always finite. They are finite when dimension equals 1 and gamma greater or equal than 1/2. By the way, can you hear me?
Yes, we can hear you.
Okay. So when the dimension is 1, then gamma has to be greater or equal than 1/2. Dimension equals 2, then gamma has to be greater than 0, and dimension greater or equal than 3. Then gamma has to be greater or equal than 0. Okay, so anyway, so Lieb-Thirring inequalities. I can repeat them a little bit later, but what they are good for, first of all, they're good for. Sorry? Slide number 4. Slide number 4.
Yes.
So they're good about while asymptotics itself, because while asymptotics usually can be obtained for, directly through the smooth, for the smooth potentials, but then you need uniform estimates of the sum of the eigenvalues to the power gamma, and then through the right quantity of the potential in order to close the asymptotic formula for arbitrary potentials satisfying certain properties. Now, Lieb-Thirring themselves, they studied Lieb-Thirring inequalities for so-called stability of matter, because they estimated basically full energy. Some of the negative eigenvalues to the power 1, it's correspond to the energy of the system and how stable it is, and then of course. Also, if we subtract from the minus Laplacian a positive potential, it drags negative eigenvalues. and then it destroys eventually to the continuous spectrum. And then where the borderline, when actually the continuous spectrum is going to be destroyed also, it's described by through the, sometimes described through the Lieb-Thirring inequalities. Then the famous problem, which is also would be applied to, it's the estimate of a dimension of attractors in the theory of Navier-Stokes equations. And that is, for example, Vishek was involved in these kind of things. And nowadays, it's also people in Moscow, they still working on these kind of things. And then also the last, which I wanted to mention, it's bound on the maximum ionization of atoms, and that is related to the fact how many electrons a nucleus can hold. And again, it's related to stability of matter in some sense, because if the nucleus cannot hold the electron, then it becomes emission, and then the matter becomes not stable. All right. So now, can you see the fifth slide?
Yes.
Can you see on the top sum of the lambda j less or equal than c constant double integral modulo xi square minus v to the power gamma negative? Is it? Can you see that?
Yes, we do.
Yeah. Well, this is exactly what Lieb-Thirring inequality is about. In fact, this is a you can integrate. You can take v out from, and then you integrate with this. You change variables and integrate with respect to psi, and you obtain this so-called Lieb-Thirring constants, you know, but and then together with the CD. Now here in this slide, I wanted to mention that if you have a particular case when a potential V is equal to minus lambda, and then equals to, when x belongs to some omega, omega is a domain in Rd of finite measure, and then it's equals to plus infinity when x doesn't belong to omega. That creates a Dirichlet Laplacian in omega, basically, and that's because of the boundary conditions are forced to be zero because of the fact that potential is equal to plus infinity. So Lieb-Thirring inequality is it's just kind of generalization of the standard problem of the study of the spectrum, discrete spectrum below lambda. In this case, the spectrum goes to plus infinity, and then we study below lambda. And that is sort of could be interpreted as a Lieb-Thirring inequalities for this particular case, for this particular class of potentials. And then there are sort of many studies of the classical Dirichlet Laplacian in omega of finite measure. And then one of them, there are sort of two major points. One of them is called Berezin-Lee-Yau inequalities, when gamma is equal to 1 or greater than 1. And we study lambda minus lambda k plus positive, to the power gamma. So we consider only those k's which show that lambda k is below lambda. And then we have this uniform inequality. The point of this kind of inequality is that they're uniform with respect to lambda. Lambda can be arbitrary, and then we would like to find sharp constants in the right-hand side. And then when gamma is equal to 0, then we study the number of eigenvalues below lambda. And this is so famous Pauli conjecture, Pauli inequality, who Pauli himself proved it, what is it, in the 60s. He proved it for so-called tiling domains. And only recently, for example, this inequality with the best possible constant was proved by a group of people. It's Filonov, Altarovich, Levitин, and Fer. They've done it for the disk, and then for the disk it was kind of a challenge for many years. All right, so this is something. Next slide, please. So
The 6.
So this is what we study: the Lieb-Thirring inequality in the form sum of lambda k to the power gamma less or equal than LD gamma integral v to the power gamma plus d over 2. And many people were involved in this, and then still new names appear. I couldn't really say mention all of these names. So what is what is known is that well, I already mentioned. I mean, this theorem said that if this inequality with a universal inequality, it's a uniform with respect to potential. That's what it is about. And then the constants L, D, gamma, which is called Lieb-Thirring constants, they are finite in cases when gamma greater or equal than 1/2 in dimension 1, gamma greater than 0 in dimension greater or dimension equals to 2, and the gamma greater or equal than 0 dimension greater or equal than 3. When gamma is equal to 0 in dimension greater or equal than 3, this is called Lieb-Thirring Zwicky-Lieb-Rosenblum inequalities, and that is of course it's related to Sobolev embedding theorems, and then also it's the case when we consider number of negative eigenvalues of the Schrödinger operator. Now, what I want to say here, and then what I want to concentrate, I was concentrating, I hope it works out. I wanted to concentrate on sharp constants, and a sharp constant basically are known for the following cases. In one dimension, then it's known that if gamma is equal to 1/2, so we can see the sum of the square roots of lambda k, then the constant, sharp constant L gamma d, d is equal to 1 and gamma is equal to 1/2, and that is equal to 1/2, and this is a sharp. And then the so-called classical constant, when you have semi-classic, when you consider, which is a constant appearing when you consider coupling constant, and when potentials are large, and you consider you put in front of potential coupling constant, and coupling constant goes to infinity, then this so-called semi-classical constant is equal to 1/4. So, but if gamma is greater or equal than 3/2, and dimension is greater or equal than 1, then you get a semi-classical constant and sharp, and it's the best possible constant. Next slide, please. So what I wanted to show you, I mean, I wanted to show you two beautiful results about these two, how to obtain these sharp constants. And then one of them is related to so-called Darboux transform, which is I mean, there are sort of at least two methods of obtaining it, but this sharp constant. But one of them is through this so-called Darboux transform due to Bengorian laws. So again, may I check whether you can hear me? Hello?
Yes.
Yeah, thank you. So what do we do? How to obtain, so what we are talking about the last theorem, and we would like to show, to consider the case, some of the eigenvalues lambda k to the power 3/2 in dimension 1. So what do we do? So consider Schrödinger operator H, and consider the lowest eigenvalue minus lambda 1, so the most the most far away negative eigenvalue, and then the eigenfunction psi1. So well, it's an elementary theorem, basically due to, well, I mean, it's just well, it's a quite elementary theorem. One can show it's a the eigenfunction psi1 doesn't change sign. It's never 0, and then it can be chosen positive, for example. So we consider logarithmic derivative of this first eigenfunction, and this is psi1 prime divided by psi1, and we can divide by psi1 because it's greater than 0. And then we consider first derivative of this logarithmic derivative, and this is we can just compute it, and we get second derivative of psi1 divided by psi1, and minus square of this f1. And if we add f1 square, then we get psi1 second derivative divided by psi, and we immediately see from the equation that it's equals lambda 1 minus b. So what we introduce is we introduce creation and annihilation operators, and this is q1, which is the first derivative minus f1, and then it's a joint, which is minus a first derivative and then minus f1. Next slide, please. Then what we have is that we can consider the product q1 star times q1, and that is we consider this product, we compute a little bit, the first derivative disappears, and then we have minus second derivative f1 prime plus f1 squared. And it's exactly the expression which you had in the previous slide. And that is exactly Schrödinger operator, but our original Schrödinger operator, but shifted by lambda 1. So if we consider the discrete part of the spectrum of q star q1, q star 1, q1, then it's because it's shifted, it starts with 0, and then it's minus lambda 2 plus lambda 1, minus lambda 3 plus lambda 1, and so on. Now, what is psi 1? Psi 1, when it's a function which is eigenfunction, it's supposed to be L2 function, and therefore, when x goes to plus infinity, assume thinking about, suppose the potential, for example, is equal to 0 outside some compact. Then, of course, you immediately can see that when you x goes to plus infinity, then solution of the Schrödinger equation has to be e to the power minus square root lambda x. And then it's because function is in L2, then when x goes to minus infinity, it has to be also decaying function e to the power square root lambda x. And in the middle, between I mean, say, when the support of the major part of the supporter function v of the potential, there is this intermediate case. I mean, then of course there are matching set of conditions, and then we get psi 1 in the end. But if we consider now f1, which is logarithmic derivative of psi 1, we immediately see this asymptotic behavior when x goes to plus or minus infinity. Okay. Now, next slide, please. Can you hear me?
Yes.
Thank you. All right, so now what we do, we just swap. I mean, that's what Darboux transform says. And it's also, that's how you deal, for example, when you compute the spectrum of classical harmonic oscillator, you just, start swapping the creation and annihilation operators. And then when we swap, then of course, in front of f1 prime, we get a different sign. And in order to compensate it, we add and subtract f1 prime. And then in the end, we get a new Schrödinger operator, which is h minus 2 f1 prime plus lambda 1. And then, of course, the new potential of this new Schrödinger operator is equal to minus 2 f1 prime minus v. So the point here is that, if you have, say, two matrices, I mean, you take, suppose you have, let me say, suppose you have q1 star times q1, and it has some eigenvalue, zero eigenvalue. Then after swapping this zero eigenvalue, in our case, this just disappears. Why does it disappear? So when I show that 0 doesn't belong to this q1 star after swapping, because if it's so, then q1, then there is a psi, function psi belonging to L2, such that we have this identity that q1 times q1 star psi is equal to 0. We multiply it by psi, and then take scalar product in L2, and we put it q1 into the other side. We get q1 star psi equal to 0, and therefore minus psi prime minus f1. Psi has to be equal to 0, and therefore psi at the plus a, for example, at plus infinity has to be e to the power square root lambda 1x, and this is not L2 function. So, 0 doesn't belong to this new operator. So the game here is the following. So we have a Schrödinger operator, slightly different. It has a potential which is minus V and minus 2 F1 prime, a new potential, and it has a lowest eigenvalue, and lowest eigenvalue of this Schrödinger operator would be minus lambda 2. So what I mean, next slide, please. So
slide number 10.
right. So it starts with the word conclusion, right? Is it correct?
Yes,
Yeah, good.
correct.
So the spectrum of this Schrödinger operator, new Schrödinger operator, it starts with minus lambda 2, and this is the lowest eigenvalue, and then there is corresponding eigenfunction, which we can actually compute even, but I mean, it's sort of through the second eigenfunction of the original operator. And of course, we can consider it again positive, and then we can sort of do the same procedure basically, and we go on. And then after n steps, we get a new potential minus Vn, which is equal to minus V minus 2 F1 prime minus 2 F2 prime, and so on, minus 2 Fn prime. And then from the what we already considered before, if we take f prime, if we take Fn prime plus Fn square, it's equal to lambda n minus Vn minus 1. So there is this recurrence here. And if, for example, we assume that potential is good enough, I mean, see, for example, from the class compactly supported and smooth, then we can always assume that there is only finite number of eigenvalues and eigenfunctions, respectively. And then in particular, after n steps, we run out of the eigenvalues, and then the discrete spectrum will be empty. Next slide, please.
Slide 11.
Then there is a trick. The trick is the following. So we take Vn minus 1 plus 2f prime n squared and integrate it. And of course, it's non-negative because the integrand is it's a positive function. Then f prime, and we can write down, we can take square simply. And when we take square, we get square of the potential n minus 1. And we take 4fn prime, and then we have vn minus 1 plus fn prime. And vn minus 1 plus fn prime from the previous slide, we can exchange into lambda n minus fn square. And magically, we can integrate f. And then we can substitute the values of f at plus and minus infinity, and we know what they are. They are precisely as we already had before. They are sort of related to this square root of lambda n's. And it's a minus infinity. Well, they are sort of equal to plus square root lambda n, and then plus infinity minus square root lambda n. And then we can integrate both terms. So we can integrate fn, and we also can integrate fn prime, we can fn prime times f squared, and then we have minus 4 divided by 3 f cubed, and then again limits minus infinity. We substitute these limits, we obtain this equation. Next equation, we compute it, and then this is what we have. And we can go on with this procedure, and then we obtain finally, we consider the same same computation with integral Vn minus 1 square with n minus 2 square, and so on. And in the end, we get all the eigenvalues to the power 3 over 2 with the coefficient 16 over 3. And that's what we obtain. We obtain that sum of the lambda to the power 3 over 2 less or equal than 3 over 16 integral v squared, finally. And this is a so-called 3 over 16, a so-called semi-classical constant. In a way, it's not surprising. I mean, that was already noticed by Lieb-Thirring in the original paper, where they considered it for stability, problem of stability of matter. And then it's related to the second integral in the Korteweg-de-Vries equation, basically. And it's there is a story behind, which I heard from Peter Lux once, who mentioned that once they were in a conference, and apparently Lieb asked him about this inequality, and then Peter referred it to the this integral of motion, of which involved also scattering data in the theory of Korteweg-de-Vries equation, and then in the end it was sort of published in the paper of Lieb and Thierry. Now, so I gave this statement and the proof of this statement, which is by Ben-Gurion laws, because in fact it could be done also in a so-called matrix case. Next slide, please.
Yes.
Yeah, but before we go to the next so matrix case, let me just mention the following. There is a procedure which belongs to Eisenman and Lieb, and that is the following. So suppose we have this inequality which we just obtained with a very good constant, which is a sharp constant. Then for any gamma greater than 3/2, we can actually get, again, a sharp constant, which depends on gamma, of course, but still it would be sharp, and it would be so-called semi-classical. And here there is a very short proof through these sort of beta functions. So, I mean, if you consider some of the lambda n to the power gamma, and then it can be written down through the Bessel functions, using the Bessel functions through this integrals, and then manipulate a little bit. I mean, and the thing is that here we have what is important is that we consider lambda n v minus t to the power 3/2, and for that in the first integral, and then here we have this power 3/2, and we know everything about the eigenvalues in this power. And we apply the previous result, and in the end, we prove the statement. So it's a very simple argument. Next slide, please.
Yes.
Now, so what here is medically that it's just one can prove similar things for gamma greater equal than 3/2, but not only for one dimension, but in arbitrary dimension. And this is our result quite some time ago. And then the idea of this result is the following. Suppose we have a M, which is a Hermitian matrix, M times N, a matrix function. And suppose we consider now Schrödinger operator, and then M is, I mean, of course, I mean, here we have the first derivative multiplied by identity matrix, and then minus M, which is a Hermitian matrix function. In L2, and then what we can obtain is that we can in sum of the lambda n to the power 3/2 of this Schrödinger operator. We have 3/16, and then we have trace an m squared running on x, and we integrate it with respect to x. So, and of course here what is important is that of course people knew that one can obtain some constant. So integral of the raise m and then take square of the whole thing. But this is not satisfactory. We need even trace of m squared. This is exactly what we need. Okay, so and the proof goes differently, not the way how Ben-Gurion laws proved it, but in the previous slides. But we do it through the this integral of motion of the Korteweg-de-Vries equation, which we already mentioned. But mind you, the Ben-Gurion laws also proved it for matrix case, but they done it a bit later. Okay, next slide, please.
Slide 14.
So what the trick is the following. So what do we do? How we can use the previous statement? Well, what I mentioned already, we can prove the following results. That the sum of the lambda n to the power gamma less or equal than with the semi-classical constant integral v gamma plus d/2 of x, and then we use the basically induction with respect to dimension. So let me just demonstrate the idea through the very simple case when we consider the two-dimensional case. Suppose we have a two-dimensional case, and suppose we have potential very good potential positive, right? And then we have a variable x1 and x2 and gamma equal to 3 over 2. So we consider the Schrodinger operator, E, and then we just Laplacian, we just rewrite in two parts. You know, we can take derivative minus second derivative with respect to x1, and then I unite. I mean, I take this second derivative with respect to x2 together with v, and then I denote this operator as a h tilde, depending on x1. And the point is that if you consider this operator, and you consider the positive part of it, then due to the variational principle, if you consider positive part of h tilde for each particular x1 here is a parameter, you consider positive part of it, then of course what happened is that you know, the second derivative with respect to x2, I mean we taken minus out, second derivative with respect to x2 has a continuous spectrum from minus infinity to 0, and then we add positive potential V, then it generates positive eigenvalues. Now, when we take a positive part of this operator, we just forget about the continuous spectrum. We take only a discrete spectrum. But due to the variational principle, when we take the positive part, we increase the negative part. And therefore, original spectrum of the operator H would go to the left, right? The negative eigenvalues go to the left, and we have an inequality in the right direction. So, and therefore, when we consider now sum of the lambda j to the power 3 of h less or equal than lambda j to the power 3 over 2, and then we have our one-dimensional Schrodinger operator with the potential, which is a matrix value, operator value, potential h tilde plus. I mean, if potential is C0 infinity, we have finite rank operator, and this is it could be interpreted as a matrix depending on x1. And then we have our inequality for matrix valued potential, and we have trace of h tilde square. And then what is h tilde square plus? This is the sum of the positive eigenvalues of the Schrodinger operator, which is the second derivative with respect to x2 plus v. And this is exactly, if you put minuses, then it's a negative part of the minus second derivative with respect to x2 minus v. And we can apply our sort of inequalities, and in particular Eisenman-Lieb sort of lifting, and then obtain in the end what we want, and it would be so. I mean, basically, and then miracle thing here is 3 over 16 with this L12, which we obtain here. This is exactly the Schraff constant, and that's sort of how we prove the multidimensional case. Okay, next slide, please.
Yes.
So now, I mean, because of all these troubles, I mean, I don't think I have much time, right? So what do we do?
Because well, you have about like 12 minutes, maybe a little more if you need.
Well, let me just maybe shorten this. Well, I wanted to show this result, which is a theorem on the square roots of lambda k. I mean, maybe, I mean, I have here the full proof, so if you ask for slide.
Professor Laptev, since you started 10 minutes later, so we can give you like 10 minutes more, so don't worry, you may take 20 minutes maybe.
You are too kind, you know, but I mean, I'm really upset that I can't really.
No problem, thank you.
Yeah, anyway, yeah, sorry, I can't do it properly. I mean, because it's the first time I do it in such a way. I mean, sorry. Anyway, so, and this is about square root. I mean, I like this proof because I think it's one of the most beautiful proofs, and it's due to Mark-Lieb and Thomas originally. I don't especially like their proof. So in the end, we had another proof which is sort of valid even for matrix cases, together with Dirk Hundermacher and myself and Timo Wild. It was published in Invenciones. And this is with a sharp constant, which is double then classical of integral V. So, and then, so there are several steps here. Let me just mention them, because it involves a lot of analysis, and it's just operator theory, and some beautiful tricks, really beautiful tricks. So first of all, if you have a compact operator self-adjoint, and if you consider modulus of the eigenvalues, then if we take some of the biggest eigenvalues, right? First biggest eigenvalue. This is a norm. One can find this kind of a statement, this proposition, the proof. It's a simple proposition, and if you look at the Archiezian and Glasman and Birman Solomiak sort of books, I mean, it's a classical result. And then what is we need from that, because I mean, the fact that it's a norm, is that we need triangle inequality in the future. So I mean, this is A plus B norm, less or equal to norm A plus norm B. That's what we need. Okay, so and then what we do, we introduce we consider Schrödinger operator, and minus lambda would be an eigenvalue. And then what we do, we take a Birman-Schwinger operator. So so what is Birman-Schwinger? So and that's sort of quite some time ago we had a celebration of Birman's birthday, and then Solomiak gave his introductory speech, and then she said, "Well, that's how you become famous. You do something very simple, and then how your name goes into history. So what is it about?" And then she made a joke about it. And then I also want to repeat this joke. So what you have is that if you have minus delta minus V n equals lambda psi, then what you can do, you can take minus lambda psi to the left and minus V to the right, and then you divide by computing psi, and you divide psi is equal to resolvent minus delta plus lambda times V, right? To the power minus 1 times V. And this is Birman-Schwinger operator. And this is what it is, And then what is important here, well, lambda was eigenvalue of this operator, right? Original Schrödinger operator. Then you can see that 1, I mean, because we have psi equals 2, 1 is an eigenvalue of the Birman-Schwinger operator, right? Now, Birman-Schwinger operator, usually people don't write this way. I mean, what you can do is take square root V times psi, and then we sort of make a new notation. And then it's better to write it in a more symmetrical way. If potential V is positive, non-negative, then you can write square root V around the resolvent, right? Around the resolvent minus delta plus lambda. And that is what we are going to do. Introduce V, W positive. W is going to play a role of square root V. And then it's we can write almost Birman-Schwinger operator. I mean, this is exactly W times resolvent times W. Epsilon square would be our lambda. But also we multiply by 2 epsilon. It's convenient to multiply by 2 epsilon. So it's kind of modified Birman-Schwinger operator. I mean, of course, this operator is non-negative, and V is positive, W is positive. So, and then what is interesting here is that one can immediately compute the resolvent, and of course, it's inverse Fourier transform of this G epsilon. And G epsilon is epsilon divided by pi times psi square plus epsilon square, and then we have forward Fourier transform and then inverse Fourier transform F star. But what is important here is that the G epsilon is the normalized measure. It's a probability measure. That is important. That's going to be important. Okay. Next slide, please.
Yes.
So that starts with lemma, the operator L epsilon greater than 0, right?
Yes.
Now, so immediately we can obtain that a trace of this operator L epsilon, because we have probability measure, we just integrate, we get its integral of W squared. And this is, if W, remember, is going to be square root of V, then it's going to be integral of V, right? Now, if you introduce a U psi, which is the just multiplication by e to the power minus I psi x, which comes with the Fourier transform, then we can prove the following proposition. When we make epsilon smaller, introduce epsilon prime, which is less or equal to than epsilon, and then we can write our Biermann-Schwinger, modified Biermann-Schwinger operator L epsilon through this following integral, where G is this probability measure, but with epsilon, instead of epsilon, you write epsilon minus epsilon prime. But it would still be a probability measure because it's a probability measure for arbitrary epsilon. And instead of L, you write L epsilon prime. So what we have is that basically when we make it epsilon smaller, eventually we make epsilon would be a lambda, say lambda 1, and epsilon prime would be lambda 2. And then since lambda n converges to 0, then they're going to be smaller and smaller, right? That's sort of the picture for the future. So we have this integral, right? Yeah. Let me skip. It's a trivial sort of computation. It's here. I mean, just some manipulation with the sort of Fourier transform. I mean, we can look at the sort of presentation of L epsilon itself, because of course, if we take G of epsilon and we take inverse, direct and inverse Fourier transform, then and it's exactly would be the kernel of the resolvent, and this is what it is, and then we can go on manipulating, and then we obtain finally this statement. But what is important here, that what we can obtain, next slide please. Well, sorry, I mean, which slide we are now on?
Monotonicity lemma.
Right, monotonicity lemma, very good. Now we are on monotonicity lemma. This is the key lemma. So, so what we have is that if because of the because now we have L epsilon, it's a compact operator, right? Biermann-Schwinger operator, modified Biermann-Schwinger operator, they're compact. And then we take the eigenvalue, the first, and it's also non-negative. We take first n eigenvalues, and this is, and if we make epsilon smaller, then we have this inequality that norm, n norm of L epsilon less or equal than L epsilon prime norm. And then, and it's concerned with exactly the first eigenvalues of these Biermann-Schwinger operators, mu, we denoted that by mu n. And this is very simple because what we have, since we have this integral representation of L epsilon through L epsilon prime, then we can write it down, and then we can put norm inside the integral, right? Because we have triangle inequality. We take triangle inequality, we put norm inside, and then of course u is just multiplication by exponential function. Their norm is equal to 1. And then and this is the end of the proof of monotonicity lemma. So this is it. Next slide, please.
Yes.
Now that's how goes the proof of the square root of lambda n less than 1/2 integral v. So what do we do? Now if we divide by 2 epsilon both sides of our modified Biermann-Schwinger operator. On the right-hand side, we have a proper Biermann-Schwinger operator. And then when we consider mu n, I mean, I mentioned before, if lambda is an eigenvalue of if lambda is an eigenvalue of the original Schrödinger operator, then the eigenvalue, the respective eigenvalue of the Schrödinger operator is equal to 1. And this is the identity star, right? And this is exactly what it is, right? So mu n is the eigenvalue of this Biermann-Schwinger operator. And then, I mean, which is divided by this constant. It's exactly a Biermann-Schwinger operator. And so this is the major point, right? So and then now we want to show the inequality, the last inequality is just at the bottom. And how do we do it? So next slide, please.
Yes.
If n is equal to 1, and then of course it's a trivial. But if n is equal to 2, we consider 2 square root lambda 1 plus square root lambda 2. And then if, of course, it's exactly equal to mu1 L square root lambda 1 and plus mu2 L square root lambda 2. And then now, instead of lambda square root lambda 1, you write square root lambda 2. And we write mu1 L square root lambda 2. And we have square root lambda 2 on the right-hand side in the first iterate and the second iterate. Right? And this is due to the monotonicity, right? Now then, we take, for example, n equal to 3, and then we instead of square root lambda 1, we write square root lambda 2 due monotonicity. And then we have mu1 plus mu2 with square root lambda 2. And again, with using monotonicity with n equal to 2, with the 2 eigenvalues, instead of lambda 2, we can write square root lambda 3. Square root lambda 2 is the right square root lambda 3. And then we have exactly the same operator L square root lambda 3, and then mu1 L square root lambda 3, mu2 L square root lambda 3, and so on. And then we go on like this. And in the end, what we have is that we have sum of this square, all the eigenvalues, and then it's just we take the trace of the L of lambda n, and then we just put x equal to y. When we take trace, we take x equal to y, just exactly what we have. And then we have w x. Well, we have this sort of integration. We have a probability measure, and then we have integral w square, and this is exactly integral. So this is the proof. I find it's amazing. I mean, think of how it sort of works out. I mean, it has a lot of features here and also a lot of tricks, and I like tricks. So that's exactly how it sort of appears. And I find this. Think about whether you could have done it yourself. You know how I think it's pretty difficult. It has to be pretty involved in order to obtain such things. Anyway, so next slide, please.
Yes.
All right. So now we've done it for the matrix case, and then sort of what we can do using this Eisenman and Eisenman-Lieb-Thirring, we can obtain this inequality for all gammas. But of course, it's interesting for those gamma which are between 1/2 and 3/2. For a while, it was the best known constant. After that, it was improved by Jean Dalbo and myself and Michael Loss. Next slide, please.
Yes.
But the latest improvement, it's a lot of work on sort of people. Of course, people are interested in the gamma equal to 1. That's a major point, and of course, gamma equal to 1 is exactly in between 1/2 and 3/2, right? So the latest result is the result with the sort of slightly less than 2 years ago, and the result of Frank, Hondermark, and Nam. And that is about gamma equal to 1 and d equal to 1. In fact, they've done it also for many multi-dimensional case. And this is so. At the moment, it's the best known constant. This is the best known constant in the this inequality for the sum of the lambda k for the eigenvalues, and this is through the integral d to the power 3/2. And of course, one can consider it also using the matrix sort of approach. And you can consider a multi-dimensional case and also for arbitrary gamma. They use the so-called ideas of Michael Lumin, a French guy who is actually was very clever to suggest some method, and then they develop it, and then finally obtain it, and then it's slight improvement. My result is Jean and Michael Loss, 2008, which is sort of we had 1.8, and this new sort of error is 1.4. And ideally, we would like to have R11 equal to 1 in dimension 3 at least. In dimension 1 and 2, this is impossible. And then nobody knows whether this constant is sharp or not. Next slide, please.
Yes.
So there are sort of two big open problems. One of them is that it shows that in dimension greater or equal than 3, then if gamma is equal to 1, we have LD1 classical. And that is, and as I mentioned already, in dimension 1 and 2, this result cannot be true. I mean, but even so, nobody knows the sharp constant even in dimension 1 and 2, and it would be also interesting to look at it. Sharp constant in Zwicky-Rosenblum inequalities are also unknown, and it's already standard since, well, I mean, it's at least 60 years, and the best constant known constant belongs to Elliott Leap. Then also, it's, as I already mentioned, that it's also all related to the Polya conjecture, and then nobody knows anything about Polya conjecture, only about a few cases. I already mentioned the last result, the sound result of Levichin, Poltorovic, and Sher, and then they proved it for the disk and then for the balls, and then even for sectors of the balls. But Polya himself proved it for tiling, so-called tiling domains. So domains which can fill the whole space without any gaps, and they don't have to be squares on rectangles, you know. But it could be very beautiful domains, but still, you know, I mean, if you're tiled, then you get this inequality. And this is a big problem, and nobody knows what to do with that for many years. And then this is sort of two big problems. And I think this is the end. Thank you very much. I mean, the last slide. Thanks.
Well, thank you very much, Professor Laptev. And we have time for questions, please.
No question. Huh? So probably I have one small question.
Yes, please.
Professor. I understand that from the physical point of view, probably the situation of gamma equal to 1 is the most important, yes, because it's, in this case, these inequalities are related to kinetic energy inequalities, yes?
Exactly, but of course, it's in a way, it's actually, it's due to the Pauli exclusion principle. And Pauli exclusion principle actually said that if you have the sort of maximum how many electrons can fill the orbit is the same orbit is just 2. I mean, they have 2 different spins, but I mean, here we forget about 2 electrons. We speak about just 1 electron. But I mean, of course, I mean, if 2, then we just multiply by 2 the whole thing. You know, it's not a big deal. But it's behind what is behind is a Pauli exclusion. Exactly.
Mm-hmm. Okay. And another question, is there a relation between these Lieb-Thirring inequalities and the estimates for the number of negative eigenvalues?
Of course, because if you have the inequality for the number of eigenvalues due the Eisenman-Lieb lifting, you can obtain the Lieb-Thirring inequalities. But then you lose constants.
Okay.
Because the constants, smaller gamma is not good constant you have. I mean, if you have bigger gamma, then you have better and better constant basically. And then you can see now what is the proof is that if gamma greater or equal than 0 or 2, then you can sharp constants. You can't prove that. But the major point now is that if small gammas, we still don't know anything about, you know. And then gamma, and then when gamma is equal to 0, Zwicky-Rosenblum inequality, the constant there, they are in principle cannot really contribute to the constant for bigger gammas because even though you get a constant, but this constant is not going to be particularly good because the constant gamma, when gamma is equal to 0, is never going to be. I don't think it's ever going to be equal to semi-classical to this sort of the, well, nobody knows anyway sharp constants.
Okay.
Thank you very much.
But you're speaking about inequalities as this asymptotic inequalities, or maybe if you estimate just part of some, you can have better result.
Yeah, well, the thing is that what my first slide, which is the bottom, couldn't be seen, because I was speaking about the asymptotics as well.
Yeah.
Sort of what happens is that if you consider Schrödinger operator, what we Lieb-Thirring inequalities and Zwicky-Lieb-Rosen and Bloom inequality, they deal with the uniform inequalities with respect to the potential. So you have, but what you can do, of course, you can put a large coupling constant in the potential. Say, suppose you put alpha, instead of v, you consider alpha v and let alpha go to plus infinity. Or you put h, which is the Planck constant, in front of the Laplacian and let Planck constant go to 0. That's the sort of equivalent. Now, and then what happened is that if you say in terms of the coupling constant increasing, you get potential bigger and bigger. And then you have more and more negative eigenvalues. And then you have asymptotic behavior. And this is the classical problem. And it comes from Weil. You have what's so-called Weil asymptotics. And then the constant there is so-called semi-classical constant. It's appearing there, and it's a sharp constant. It's not, I mean, whatever uniform estimate you do, you cannot get better,
Okay. Okay, thank you. Thank you very much. Maybe more questions? So, if no more questions, then let's thank speaker for very nice presentation.
Thank you for inviting me.
Thank you,
very much.
Professor Laptev,
Thank you.
for delivering such nice talk at our seminar. Thanks to everyone who came to our seminar, and see you in 2 weeks. Thank you.